Okay, now let us discuss the second thing that a link layer should provide to be used in the internet if the link layer uses shared medium. We know that these technologies use MAC addresses to deliver frames. Unfortunately, the only address that the internet understands is the IP address. The problem with the IP address is that it doesn't make the delivery happen, though. Let me take an analogy. Suppose you are calling your friend. Do you use your friend's name to call her? It looks as if it is the case, but that's an illusion. The only address that the telephone networks understand is the phone number. So to call your friend, you need her phone number. Today's phones are smart, but they cannot make a call using only your friend's name. So it translates the name into the phone number before making the call. And just like that, on a shared medium link, knowing the IP address of the next router does not let you move your IP datagram to the router. You have to figure out the MAC address of the next router, and then you put that in the destination MAC address field of the link layer frame. Then you can deliver your datagram that is contained in the payload portion of the frame. Any computer that is connected to a shared medium link has a translation table, translation from IP to MAC. Every machine needs one if it is using a shared medium link. Your smartphone needs one if it is using Wi-Fi, for instance. There is no exception. Here I show a translation table. The translation table on my Windows computer. The command I use to see the table is ARP, A-R-P, -A, which tells the computer, hey, I want to see all the entries in the IP to MAC translation table. In this table here, the first column is the IP addresses of the computers you may want to talk to over a link. There could be many such machines, since this is a shared medium, right? On the second column, there are corresponding MAC addresses. So, for instance, if the IP address of the machine that's over a link is 163.152.23.1, this computer somehow knows that its physical corresponding physical address is 00D095864F2D in hexadecimal. Well, how does my computer know these mappings? Well, that's a good question, and we will learn in one of the following sessions, but the protocol used for it is called the Address Resolution Protocol. So the shared medium type link layer that wants to be used in the internet should support Address Resolution Protocol so that the translation table can be built by it. Finally, the third thing that a link layer has to support is the management information base. For example, look at the ifconfig out here. It shows the data values associated with the Wi-Fi link on my smartphone, and it shows some statistics here, like number of received packets, number of transmitted packets, number of received bytes, and number of transmitted bytes, number of errors, number of dropped packets, and so on and so forth. In fact, there are many more data that this link is bookkeeping for network management. When some monitoring node calls in and asks how many packets have you received so far, for instance, this Wi-Fi device will answer because it is collecting these data. For remote management using internet protocols, all entities, including the link layer devices, should provide the data. And the collection of such monitored data is called the Management Information Base, or MIB, or MIP in short. We will learn about it in a later chapter. Now we are ready to introduce the notion of interface, which is the central theme of the second part of this session. When a computer is connected to the internet via a communication link, the link has a hardware component and a software component. We discussed that earlier. The former corresponds to the physical layer and the lower part of the link layer. The latter, on the other hand, exists inside the operating system and has a representation in the kernel. This representation is called the interface, and it represents the communication link for the Internet protocols in the kernel. In fact, the Internet protocols do not know and do not care about the physical layer and the lower link layer component. For them, this abstract representation called the interface in the kernel is all there is to know. The actual bonding of this representation and the corresponding device is up to the operating system to configure. And whenever we refer to quote-unquote interface in the context of the Internet protocols, it never means the hardware, but it means the abstract representation in the kernel. In fact, the ifconfig output that we saw earlier is obtained from this interface in the kernel. What is most interesting is that the interface, the representation in the kernel, has IP addresses in it. So when we give an IP address to my computer, that value actually goes into this data structure here. Other data items here, there are MTU sizes and the statistics we just saw, used for remote management, and last but not least, it has the pointer to the driving routine for the hardware of the communication device. Here is another example of the interface, the logical representation of communication links on a Linux computer. Here I use the netstat command, network status, -i option, which lists up the communication interfaces. It only shows some aspects of the interface, say the MTU size, the logical name, the number of received packets, some errors, and the flags. It says they are from kernel interface table. So the output clearly tells us that it is showing the kernel interface table. It has two entries, ETH0, that means Ethernet number 0, and LO, which stands for loopback interface, that we will talk about in a few slides. And we see here that the MTU size of the Ethernet interface is 1,500 bytes, obviously. As to the loopback interface, well, there are not many packets exchanged using it, and most of the packets are through the Ethernet interface. And there are flags where the meaning of each of these characters is given in this table. B means here, B for the Ethernet interface, B means broadcast is supported on this interface. It tells us that the Ethernet interface supports broadcast, meaning that it's a shared medium type link. And R and U, U means that the interface is up, and R means the interface is running. And L is it says that this particular interface is a local loopback interface. There is a difference between U and R here, although usually you will see these two flags appear together. It basically means that the interface is up and running, but U, the interface is up, is different from R in the sense that U means that the operating system has allocated resources for this interface. It doesn't mean that the interface is actually connected to the network. But if you see R there, it means that not only the resources are allocated to the interface is also connected to the network, so it's fully operating. Okay, yet another example from Windows system. Here I use Nest Shell interface IPv4 command. It shows the state and the MTU sizes of each interface, and it also shows the names of these interfaces. Okay, so nothing really special, but we see that the MTU size of the loopback interface is quite large. It's 4 gigabytes. It is not surprising because the loopback is a special interface that only exists as the kernel data structure without the corresponding hardware. Therefore, there is no limitation on the packet size imposed by the hardware. Okay, yet another command that shows other aspect of the interface. Here I use ipconfig command on Windows, and it shows the IP address of the interface and the subnet mask, which we will discuss later on, and the default router address in one of these interfaces. The default router connected to this computer. Well, here I show the Linux kernel code snippets that show the data items in an interface has. In particular, you can see the list of IP addresses that this interface has, and the pointer to the device driver routines for the interface. Well, here we finally get to talk about the mythical loopback interface. I already mentioned that the loopback interface is only a logical one, different from other interfaces that have corresponding communication hardware. To understand why we need this special interface, we need to think a little bit more about why we use Internet protocols in the first place. Well, the answer is we want to make 2 or more running programs or processes to talk to each other. For instance, we want the web server and the web browser to talk to each other so that we can see web pages. We want the mail server and the mail client to talk to each other so that we can send and receive emails. We want the game server and the game programmer on your smartphone to talk to each other so that you can enjoy, say, the Battleground game on your smartphone. So the Internet protocols exist for process-to-process communication, or inter-process communication, IPC in short. These processes, by the way, can be anywhere on the globe. The processes, these communicating processes, are usually far apart, like 26 hops away, that we saw in the case of University of Pisa website. However, sometimes the processes can be on the same machine. Still, the Internet protocols can be used for inter-process communication between these processes. Basically, the Internet protocols do not care where the processes are located. It is actually a beauty of using the Internet protocols for inter-process communication. In case the 2 processes reside on the same computer, however, IP datagram from the sending process does not have to go out to the Internet and come back to the receiving process. Instead, the IP datagram can be bounced back by some interface in the kernel to the receiving process, right? That is why we have this special interface called the local loopback. Here I show you the ifconfig output for the loopback interface on my smartphone. Okay, the logical name for the loopback interface is LO, and it clearly says it's a loopback interface. And in this case, the MTU size is set to 64 kilobytes. So again, this is how the loopback interface is used by the 2 processes on the same machine. Okay, so process A and process B, when they communicate, they do not have to go out through LTE and come back. Okay, that is going to be a waste of resource here. So instead of doing that, you can set up a loopback interface inside a kernel, and this loopback interface can, send it back, bounce the packet back to the receiver process. For IP, these interfaces, it can have many interfaces. On my smartphone, I have LTE, Wi-Fi, loopback. On my PC, I could have Ethernet and I don't know, Wi-Fi sometimes. So for IP, these interfaces are like doors to the internet, open to the internet. On my smartphone, for instance, the operating system has these 3 interfaces, and it can choose one of these interfaces to send out an IP datagram depending on, say, interface state and the destination. For example, when Wi-Fi is available on my smartphone, the IP on my smartphone does not use LTE. To save money, it uses Wi-Fi. But if Wi-Fi is not available, it's not usable because there is no AP that is close, then it changes to LTE. Or the choice of interfaces, the choice of interface could depend on the destination. For instance, one example was the loopback interface. Okay, in this case, IP chooses loopback instead of LTE or Wi-Fi. Okay, so it's time to wrap up. We have discussed what IP should know about the link layer first, what the link layer should do to be used in the internet, and how such link layers are abstracted by the kernel so that IP can handle them as logical representations called interfaces. And we learned that the interfaces are like doors for IP, among which you can choose to go to a given destination. Finally, here are some commands you want to try on your computers. Please go for it and get to know the internet under the hood. See you in session 3.